Last page, we have an overall reaction. AB plus C goes to ABC, overall reaction. And it wants to know, is this a valid mechanism for the reaction? Knowing that the reaction is second order with respect to AB and zeroth order with respect to C. So that means that the rate law for the reaction is going to look like AB to the 2, C to the 0. So for the mechanism to be valid, we need to look at the slow step. The slow step is this one right here. And the slow step is the step that determines the overall rate law for the reaction. So what is the rate law for the slow step? In an elementary step, the rate law for an elementary step is given to us using the coefficients, stoichiometric coefficients for that. So since we have AB plus AB, we have two ABs. There's the rate law for the elementary step. And what we're being asked is, does that match up with the overall rate law for the reaction? C to the 0, anything to the 0 is 1, so that term can just drop right out. And so yes, this is going to be a valid mechanism. For that reaction, what are the intermediates? Remember, the intermediates are not reactants and not products. So if we're going to look at our elementary steps, our mechanism, AB is a reactant, which means it cannot be an intermediate. C is a reactant, so it cannot be an intermediate. A is a product, it cannot be an intermediate. BC is a product, can't be an intermediate, which means that our intermediate is AB squared. Again, the intermediates are things that are not products or reactants of the overall reaction. Question 19 is a nuclear chemistry question. What atom is produced after radon 220 undergoes 2 alpha decay reactions, followed by 2 beta decay reactions? So we need to start by writing this out, and we're going to need to find a periodic table that's going to give us the atomic number for this guy, 86. So 2 alpha decays, that means we're going to be spitting out 2 heliums and 2 beta decays or electron decays. So that means we're going to be spitting out 2 of these guys as well. And then we're going to be making something out here. And the question is asking us what shows up out here. Well, remember that we're doing like a conservation of atomic particles, subatomic particles. So we've got a total mass number of 220 on the left, which means that our total mass number over here on the right needs to also be 220. We've already accounted for 8 of those mass number units. 220 minus 8 is going to be 212. So we know whatever this guy is, it's got a mass number of 212. And then for the atomic number, we're going to conserve that as well. So we have an atomic number of 86 on the left side, and that means that over here we need a total atomic number of 86. Right now we have 2 plus 2 minus 1 minus 1, so we have 2. So that means we need an atomic number of 84. And then what you're going to do is go to your periodic table. You're going to find which atom is atomic number 84. There's that guy's identity. And the last problem is about radioactive decay. We have a dosage of 0.05 micrograms with a half-life of 6 hours. How long does it take for the initial dose to get down to 1 times 10 to the minus 3? So for this problem, you are going to be using the radioactive decay equation, which is first order instantaneous rate law, but it's been rearranged a bit to make it work better for these types of problems. We know the initial amount, which is N0, is 0.05. And we know that the final amount is this 1 times 10 to the minus 3. And the question is, how long does it take? That's our time. That's what we're trying to figure out. What about K? We need, the only other variable in this problem that we have to figure out is K. We can get K from the half-life. T1 half equals 0.693 over K. We know that the half-life is 6 hours. So if we rearrange this equation, we get T1 half times K equals 0.693, and then we get K equals 0.693 divided by T1 half, and then we just plug the half-life in, 0.693 divided by 6 hours. That's going to give us our rate constant, 0.693 divided by 6. Our rate constant is 0.1155. And we do want to be thinking about the units here so that we can put the right unit on our answer. Now we are ready to go back to this equation right here and start filling it in. N1 is 0.05 and 0 is 1 times 10 to the minus third. And I'm not worrying about the units here because the units are just going to cancel each other out in this division. Those look like decimal points now. I need to erase those. Our rate constant is 0.1155. Don't forget the negative sign. And our time is the variable that we are trying to solve for. So we are going to get 0.05 divided by 1 times 10 to the minus 3. Take the natural log of that. 0.05 divided by 1 times 10 to the minus 3. That is 3.9. I've put them in this equation backwards, didn't I? I was wondering why. My answer should be a negative number. It is 1 times 10 to the minus 3. That's our n sub 1 divided by 0.05. 1 times 10 to the minus 3 divided by 0.05, and take the natural log of that. That is much better, negative 3.9, and that is equal to negative 0.1155 inverse hours times the time, 0.1155. Time is 34 hours.